walking me through the process that you're drawing in class, but like with like the pentose and.
Oh, with the
granulates?
pentose phosphate and see how everything branches off?
Yeah.
Because I probably would have got through most of it if we had an hour drawing it out. So, does that sound okay?
When do you go to class?
The whole cycle,
Oh, like from.
from like beginning to.
Oh, okay. That's art.
You see this circle?
It's a circle of death.
It's a nice circle.
What?
It's like the sun. It's like a donut.
What is it? The protractor? Did you use a protractor on that?
Somebody left already, huh?
You lost 2 already.
Oh, man.
Yeah, you taking too long.
You're not here enough. Pick it up.
Okay, crap.
Where's your dance?
Where's my dance? All right.
I'll show him.
Okay.
How into depth are we gonna need to know the name of all the things in all the pathways?
As best as you can.
Yeah.
It's
Very
relative.
concise, right?
I know
Alright. So,
I'll
do your
like,
best.
don't know any of the names, I'm like, I tried my best.
hey, here's the thing. You only need to know really, I think it's 5 names.
Okay.
Glucose, fructose, glyceraldehyde, dihydroxyacetone, glycerate, pyruvate. 6. 6. All you have to do is put the prefixes with it. So glucose goes to glucose 1-phosphate, or 6-phosphate, right? So glucose is the name, right? And then glucose 6-phosphate goes to fructose 6-phosphate. Then we get fructose 1,6-bisphosphate. But you only need to know 6 names. It's just the phosphates and stuff
And then you
change
get the
everything, right?
160
So,
phosphates.
You know the structure you can name.
all right, yes, so I think you guys can handle the name. You're a biologist, come on, you've memorized glycolysis from the name. You knew nothing about the structure probably, right? They didn't have you memorize this stuff? Okay. So,
We're all scientists with the exception of Greg.
all right, so
What's great?
glucose transfer.
Oh my gosh. Is
Okay.
that a real science?
Don't worry, Greg. I have to do
Look how big his forehead is. And then we'll make this look realistic. Here's the blood. Okay. All right. So I'll hit glycolysis, but you want to see where things are diverted, pentose phosphate pathway, and stuff like that. So we've kind of already, during class today, we went through the whole pathway, except we didn't do electron transport. But then the question is, what about the things that divert from glycolysis? So how do we think about drawing those?
Can we put another screen down as well? Or
I don't think I can. No, I don't think I can. Because it's on automatic thing. As soon as I turn that on, the one that goes down goes down. Let me see. And they only have one projector. So they designed the room maybe to have a second one, but it doesn't work out. Yes, the engineers designed it. We're in an engineer building and we're kind of great. Anyways, no, I'm getting on everybody today. The biologists, the engineers, okay.
Psychology.
I like biology.
Psychology,
don't
Greg.
I like
Definitely better than engineer.
Okay, so we get glucose inside the cell. Now it can go different pathways, right? It goes inside, step 1 commits it to the cell. And that's our phosphorylation. So, ATP, ADP. And we get glucose 6-phosphate. So this commits to the cell. Purpose, very negative LPG. Okay, now from here it can go on either potentially to glycolysis through the isomerase. First we'll make fructose 6-phosphate, right? Via the isomerase. Fructose 6-phosphate, okay? Okay, and that's our pathway to glycolysis. Let's just go here and say, well, what commits it to glycolysis? Step 3, phosphofructokinase. We'll take ADP. We'll phosphorylate that one position. And we get fructose 1,6. And if you have 2, you just say bis. That's all there really is to bisphosphate. Anytime you have 2, you just say bis. Okay. Now, that's committing it to glycolysis. So, step 2, step 3. Commits to glycolysis. Which makes sense. You're investing your final ATP, right? And if you're going to invest that final ATP, you better make sure you want to send it there. Okay. Now from here, this glucose 6-phosphate up here, can go different pathways because it at this point is not committed to anything but the cell. Okay, one of the pathways is the pentose phosphate pathway, which is composed of 2 parts. The oxidative pathway, okay, and then the non-oxidative pathway. So let's look, first you undergo the oxidative pathway. So, and remember this pathway's purpose is to produce NADPH from NADP+. And the first step is to oxidize this hydroxyl here at the carbon 1. We make a lactone ring. But everything else stays the same. And that's the first part. The second part is to open it up to make the carboxylic acid form of glucose. So we're just going to bring in some water, which would attack the carbonyl on the enzyme. It would pop that thing open, and then we would get our gluconate. Gluconate 6-phosphate. So now we have our carboxylic acid. The rest is just like glucose. It ring opens. 1, 2, 3, 4, 5, 6. Keep our phosphate on there. Everything else looks like glucose. Now the reason for getting this carboxylic acid, remember those are good leaving groups. And we've seen that in citric acid cycle, right? Where you make these, you can completely oxidize the carbon and steal away electrons. So you see the same strategy here in the pentose phosphate pathway. We're just going to, I'll finish this out. And we're going to make ribulose. We're going to kick out here. We're going to put in NADP+. We're going to get NADPH out and CO2. And we're going to make ribulose. 5 phosphate. Now ribulose is the ketose form of ribose. Just remember all the hydroxyls are on the right hand side. Now, this is, say, oxidative pentose phosphate, and what you're seeing is the same thing that you saw from the citric acid cycle. Steal electrons, but now we're, instead of NADH, we're sending it to NADP, which just has a phosphorylation difference. And we're using CO2 groups as good leaving groups to snatch our final electrons. Same thing that happens via step 3 and 4 of the citric acid cycle. Okay. So that's our oxidative pathway. Now from here, this can go different ways. We can convert this, and I'm just going to draw it as an arrow, via an isomerase, this way. Isomerase. What we're going to do is we're just going to make ribose. Ribose. It's just the aldose one. Okay, and then that can be used to make DNA and RNA, right? That's the building block. Straighten that up a little bit. So isomerase can get you to ribose 5-phosphate. This is ribulose 5-phosphate. Okay, so through the oxidative pathway, we can get ribulose, and we can either process it and send it this way to become ribose, which can eventually become DNA and RNA, or we can do a recycling process called the non-oxidative pathway that will recycle these 5 carbons of ribulose, and we will make 6 carbons. But in order to do this, we need to send 3 through. Okay? So let me do my stoichiometry here, and we'll look at the non-oxidative pathway. So if we put 3 of these in, three of those, we get 3 of these out, and we're just going to put that at each step. Now the reason we pick 3 is because 3 times 5 equals 15 carbons. And what this allows us to do is get 2 times 6 carbons and 1 times 3 carbon molecules. So we can recycle these back into 6 carbon and 3 carbon molecules. Why 3 carbon molecules or 6 carbon? Because they can be used here, or they can be dumped back into the glycolysis, because it uses 3 carbons, right? Glyceraldehyde 3-phosphate, dihydroxyacetone phosphate. Those are both 3 carbon molecules. So if we want to continue to generate more reduced cofactors for biosynthesis, instead of sending it this way, what we'll do is we'll do a recycling process here. Okay. And I'm going to draw this kind of over here. Is everybody okay with that? Okay. So, in order to do the recycling process, I'm going to kind of, I'll draw it over here to kind of show this process. Okay, we're going to make ribulose. We're going to have to make it into 2 different things. One of them is ribose. So ribose, which we have up there. And I'll do it in this color just to differentiate it. 2, 3, 4, 5. Okay, so one of the molecules out of 3 is going to be converted to ribose. The other one is going to be converted into xylulose. And I'll show you that's just an epimer. So this is done by an isomerase. And over here, we're going to do an epimerase. And we're going to convert this to xylulose, which is just taking ribulose and flipping the hydroxyl at that 3 position. Okay. And that's only one out of those 3. We'll actually make a second one of those. So this is xylulose 5. And I'm just going to use PI instead of keep saying phosphate. Okay, so then here's the process. We have to get back here to glucose 6-phosphate. Get out my pointer. You can't see my finger on the screen. Okay, we got to get back to here, glucose 6-phosphate, so we can continue to pour through this pathway. So what we're going to do is we're going to start combining carbons from each of these to get back through here. Okay? And so we're going to do a 2-carbon, 3-carbon, 2-carbon transfer via what we call transketolase and transaldelase. These are enzymes that do this. So here's how we're going to do this process. I'll give you some different colors here. So this is going to go here. Let's see if this will all work out together. And we're going to say this part goes here. Now what happens is a transketolase is going to clip off, okay, using TPP, thymine pyrophosphate, clip off these 2 carbons and add them to the aldehyde carbon. And we're going to make cetoheptulose. So what happens here is we get out here, oops, sorry, color scheme. I'm going to take those 2 carbons from there, 1, 2, okay, and I'm going to make a ketone. It's going to get added to the ribose. And so what do we get? And that's what I'm trying to show you with the color is, okay, this is where those carbons are. 1, 2, 3, 4, 5. And that's the cetoheptulose. Cetoheptulose 7-phosphate. And then what was left over from ribulose goes down here. 2, 3. And we make something that we're all familiar with, glyceraldehyde 3-phosphate. Cool, that can be used in glycolysis, or we can just keep going. This was done by a transketolase enzyme. Okay, but we have not made our 6-carbon molecule yet. So what we're going to do now is cut off 3 carbons from here, transfer it back there onto this carbonyl, and we're going to make fructose 6-phosphate. So let's draw this. See what color I got here. So we're going to get here. fructose 6-phosphate. Oh, shoot, I put that oxygen on there. Sorry. Okay. So fructose 6-phosphate. Now what can happen with that? Well, we can just, I'll use a different color here. We can just recycle that, right? Here's fructose 6-phosphate there. Right? We can send that back up, use the isomerase, and we can make glucose 6-phosphate again. So that gets sent back, and we can use our isomerase to convert it back into glucose 6-phosphate. Okay, now we're left with something here. Erythrose, which is a 4-carbon. So we have here now 2, 3, 4. Okay, and erythrose is it all behind? I'm just going to put my phosphate down here. I'm not showing you the hydrogens because I think it's more confusing. All right. So we following so far? Now all we have to do is bring in another xylulose. Right? We've sent in a couple here. Let me see what's the best way of doing this. I'm just going to bring it in over here. So we'll bring in here another xylulose. And if we wanted to say where it came from, right? We could send this. I know it's getting kind of crazy, but that's where it would come from. It would go through that epimerase, and then we would get a second one over there. That's where you would see it from. I'm just going to erase it because I think that's just confusing. Okay, now what happens? Okay, we're going to do another transketolase. We're going to take 2 from here, and we're going to attach it to here. And we're going to get out on this side. Glyceraldehyde 3-phosphate. Okay, which we can send over to glycolysis. And up here. Yeah, this is fun. Okay. Make this a little shorter. As you can see, this is not planned. Yay for you guys, right? So we'd say 1, 2, 3, 4. And then we would get our 2 here. And then you get your fructose 6-phosphate. So again, this is F6P. And then where does that go? Same place. We can send that over here. Use the isomerase to go back. Okay. Let me see if I can. Can you see that all up there? I'm going to zoom it up and I'll pick it up. But that's what's happening. Can you guys see it? So, okay, we have our xylulose and our ribose. Cut off 2. put it on there, we get 7. 1, 2, 3, 4, 5, 6, 7, okay. Got 7 plus 3 is 10. We put 10 in, okay? But none of those look like glucose or fructose. We actually make fructose. Now we have 3 here, glyceraldehyde 3-phosphate. Cool, if we can put 3 more on there, then we can get to fructose or glucose. So we chop off those 3 from there, attach it here, and we get fructose 6-phosphate, which we can make into glucose 6-phosphate just via the isomerase from glycolysis. So we got 1 of them. That left us with this 4 carbon, 1, 2, 3, 4. If we can just add 2 more carbons to it, we get 6. So we bring in another xylulose. So 1, 2, remember we had 3 up there. And we chop off 2 from that, use the transketolase, attach it here, and we get our fructose, our second fructose. And we have glyceraldehyde 3-phosphate left over. Everything that can be shuttled back through glycolysis or back through the pentose phosphate pathway. So this is known as the non-oxidative pathway. Of the pentose phosphate. And the purpose is to recycle those 5 carbon sugars back into 6 carbon sugars that can be either used for glycolysis, or you can continue to run them back up this way and continue the cycle through, so that you can continually get these NADPHs. Does that make sense? Can you all see it? Are you overwhelmed? It's okay. Welcome to my world. Anyway, so that's how that pathway works. The oxidative pathway is easy. You guys can do the oxidative pathway for sure. But that's what's going on. It's really just a recycling pathway. The non-oxidative pathway is, hey, we don't need to synthesize DNA or RNA. We need reduced cofactors for reductive biosynthesis. So remember, that's the purpose for this pathway, is to get reducing equivalents for reductive biosynthesis, where you use electrons to reduce a molecule and build something new. Well, if we have a lot of biosynthesis we need to do, let's just keep recycling this over and over and over and over. And then what do we get? We get more and more reduced cofactors that we can use. I wish I could zoom out on this a little bit. Pretty nice. So is everybody okay with that? It doesn't matter if you're okay with that, but does it make sense? Okay, so that's one way that glucose can go. Now the other way